Okay, this is part 2 in a lecture for concave mirrors. Specifically, now we get to the math. The math comes in 2 parts. The first part is locating the focus. That is, where is the focus of the spherical concave mirror in relation to the geometry of the mirror itself? In order to find where the focus is, we have to draw out the following situation. We form the image of a point object at infinity. So let's look at one of the previous diagrams from the previous video. Okay, so now we get to the math, and the first thing that we do is we find the focus. Okay, so right here is the spherical concave mirror. Okay, right here is the optical axis, like so. Let's just immediately locate the focus like this. And now in order to form the image of a point object at infinity, recall that all of those incoming light rays are parallel to each other and parallel to the optical axis. I only need 2 of the light rays, however, for this derivation. Okay, the first light ray we'll just draw like so along the optical axis itself. It then reflects upon itself like so through focus. And then let's use this top light ray right here like so. Okay, this guy also reflects through the focus. Like so. Okay, now, this distance here on the diagram, this right here is the focal length. What we're trying to do is find the relationship between the focal length and the geometry of the mirror itself. Okay, this point on the diagram is referred to as point A. This point right here is referred to as point B. Okay, now right here at this location, let me go ahead and draw in the normal line, which is perpendicular to the mirror's surface at that location. That's like so. And I'll extend it here back to the optical axis itself, and we end up with this point right here. Because this dotted line here is perpendicular to the mirrored surface of this location, this then means that this right here is the center of the sphere. This is referred to as C. This distance here then therefore is equal to the radius of curvature. This is just simply referred to as small r. Okay, now right here at point B, this angle right here is the angle of incidence, call it theta. Therefore, this angle here is the same thing. This right here is the angle of reflection. Once again, that's just the law of reflection. Okay, now right here at point B, take this red line, which is parallel to this one, and extend it like so a little bit back behind the mirror. Okay, do the same thing with this black line. Take this black line and extend it back behind the mirror a little bit, like so. And then in terms of alternating interior angles from geometry, this angle right here is the same thing as this angle right here. That's, of course, the angle theta. Because this black line, however, is the same thing as this, and this red line here is parallel to this then means that this right here is also the same angle theta. So if you look carefully on the diagram, take a look at triangle CFB. Notice that triangle CFB is isosceles. Okay, now because that triangle is isosceles, this then means that the following 2 sides are the same thing, CF and FB. So therefore, CF is equal to FB. Now here's where we ignore spherical aberration. If you're talking about a parabola, then this distance here, FB, is the same thing as this distance here, FA. That's not quite the case if you're talking about a sphere, but as I said, we're ignoring spherical aberration. All right, so then therefore, this distance here, as I said, FB is about the same thing as FA. Okay? Okay, now, CF and FB are the same. FB and FA are the same. Therefore, FA and CF are the same. So if this right here is the radius of curvature, and this right here is the focal length, well, the focal length is the same thing as this. This then means that the radius of curvature, very simply, is twice the focal length. So the focal length itself is just 1/2 the radius. Easy enough. That's the first part of the math, locating where the focus is. It's just 1/2 the radius of the sphere. Okay, the second part of the math involves deriving what is known as the mirror equation. The mirror equation is a relationship between three very important distances when talking about mirrors: the object distance, the image distance, and the focal length. The mirror equation can be derived for any situation involving any mirror, but I'm going to go ahead and derive it by using the spherical concave mirror for an extended object that is close to the mirror. Okay, let me do some erasing. Okay, so next, we derive the mirror equation. Okay, draw this diagram nice and large in your notes. Okay, so right here is the spherical concave mirror. Right here is the optical axis like so, right angle. Let's go ahead and put the focus here like this. Okay, now I'm going to go ahead and take my object, my arrow, and place it fairly close to the mirror. I'm going to go ahead and draw it here. Okay, and then I'm going to use the same two light rays that you saw in an earlier diagram to first of all form the image. So first of all, coming off the tip of the arrow, a light ray that is parallel to the optical axis, it then reflects through the focus like so. Okay, then draw your second light ray backwards of the first. That is coming from the tip of the arrow and passing through the focus like so. This then reflects parallel to the axis, like this. And then right here is where the image of the tip of the arrow forms. Right here is the real inverted image like so, like in one of my previous diagrams. Okay, now for purposes of this derivation, we need one more light ray as well. What I'm going to do is draw a light ray from the tip of the arrow, and then I'm going to draw it down here to the center of the mirror like so. When I do, right here is the angle of incidence because the optical axis is the normal line at this location, and then therefore I can easily reflect that light ray at the same angle on the other side of the axis. When I do reflect it, it has to pass through the image, like so. Right here is the angle of reflection. Okay, now a bunch of things here are labeled on this diagram. First of all, points. This point right here is referred to as O. This point up here is referred to as O prime. This is called point A. This is called point B. And then right over here, this point here is referred to as I. This point down here is referred to as I prime. And then we have three distances here that are important. The first distance is the distance that the focus is from the mirror. This right here is the focal length F. And then we have right here the object distance, the distance that the object is from the mirror. Just like when talking about plane mirrors, this is referred to as DO. Okay, and then we have this distance right here. This is the distance that the image is from the mirror. This is referred to as DI. And now on this rather messy looking diagram, basically what we end up with are two sets of similar right triangles. Okay, the first set is as follows. Take a look at triangle O prime, A, O. O prime, A, O. And then take a look at triangle I prime, A, I. Triangle I prime, A, I. Notice that those are two right triangles and they have the same angle here, for example. Therefore, they're similar to each other. When they're similar to each other, they have the same ratio of sides. Okay, now one thing, by the way, I still have to label in this diagram before I write down these ratio of sides is the following. This right here is referred to as the object's height or size. This is called HO. This right here is the image's height or size. This is referred to as HI. Okay, now here is the ratio of sides. What I'm going to do first of all for this top triangle like so is do the following. Take HO over this distance here, which is DO. And then for the bottom triangle, that's then therefore equal to HI divided by this distance here, which is DI. Once again, similar right triangles, therefore same ratio of sides. Okay, now here's the second set of similar right triangles. Take a look at triangle O prime F O, and it forms right here this black angle. So O prime F O. Okay, and then take a look at sort of triangle BFA, wherefore BFA right here is the same black angle. Now, is BFA, strictly speaking, a right triangle? Not quite. There's a little bit of curvature here, but we're ignoring spherical aberration. So then, therefore, triangle BFA is similar to O prime FO. Therefore, they have the same ratio of sides. Now, for this top triangle right here, what I'm going to do is take HO divided by this. This distance here is DO minus F. That's this guy right here. So HO over DO minus F. And now for triangle BFA, we have this distance here, which is HI divided by this distance here, which is F. Like so. So I end up with, as I said, two sets of similar right triangles. They have the same ratio of sides. What I'm going to do for each set is I'm going to write each set in terms of HI over HO. So let me do that first of all for the top set. So for the top set, HI over HO is DI over DO when you cross multiply. Do the same thing for this right here. Write this as HI over HO. So HI over HO, and when you cross multiply appropriately, you get F over DO minus F. And now take the two right-hand sides here and set them equal to each other. Like so, and you end up with an expression here that relates the three distances to each other. If you algebraically rearrange this expression a little bit, you end up with something that's really easy to remember, and this is referred to as the mirror equation. Here's the mirror equation when you, once again, rearrange this guy right here algebraically. 1 over DO plus 1 over DI is equal to 1 over F. It's actually really easy to remember. We also define what is referred to as the magnification. The magnification is referred to as M. By definition, it's the ratio of the image size to the object size. However, from the math that we just went through, it's the same thing as the image distance divided by the object distance. And then lastly, in order to take into account any situation associated with any type of mirror, we have to give this expression a negative sign. Okay, now why is there a negative sign there? Why did I do that? Well, when you use the mirror equation and the magnification expression, there is a sign convention that is used. This sign convention makes the expressions applicable to any situation involving any mirror. When I initially write down the sign convention for you, you're going to look at it and go, huh? But when you start to use the sign convention in basic examples, it makes perfect sense. Well, let me go ahead and write it out first. All right, so the hard part's over. Erase all this junk. Okay, so as I said, let me just go ahead and write down the sign convention first, and then we'll begin to apply it. Okay, first of all, the object distance DO. The object distance DO is a positive number if the object is in front of the mirror. However, the object distance can also be negative if the object is behind the mirror. how can an object be behind the mirror? That doesn't make any sense. Well, an object can be behind a mirror if it's a mirror combination, because the image of the first mirror becomes the object for the second mirror. And if that object is behind the second mirror, then it's a negative number. You'll see this in an example involving telescopes later on. Okay, and then we have the image distance, di. Okay, it's a positive number if the image is in front of the mirror. This then means that the image is real. However, the image distance is negative if the image is behind the mirror. It's then therefore virtual. Okay, and then lastly is the focal length. The focal length is a positive number if the mirror is concave. It's a negative number if the mirror is convex. We'll see that a little bit later on. Okay, once again, when you initially write this down, it doesn't appear to make much sense, but now let's immediately begin to apply it. So at this point, go ahead and write down the first of today's lecture examples. This is basically the concave mirror problem. Okay, let me go ahead and read it to you. A concave mirror has a radius of curvature of 20 centimeters. What is the focal length? And then for the following values of the object distance, calculate the image distance, magnification, and draw the ray diagram. And you do have to be able to draw the diagrams in order to receive full credit. Okay, now the image or the object distances that are given here in the problem are 20, 10, and 5 centimeters. So we're taking an object and just getting it closer and closer to the mirror. Okay, now off to the side here, let me just go ahead and write down the mirror equation, like so, and accompanying it, the magnification expression, like so. Okay, and then what we do here, first of all, is we find the focal length. The focal length is 1/2 the radius of curvature. The radius of curvature is given to us as 20 centimeters. Therefore, the focal length is 10 centimeters. It's a positive number. I'll put a plus sign there for emphasis because we're talking about a concave mirror. Okay, now part A of the problem, the object distance DO is given to us as positive 20 centimeters. And you just keep everything in centimeters for a problem such as this, that's perfectly fine. And now you just follow the math. Calculate first of all the image distance DI, and then calculate the magnification. The numbers that you end up with, that then tells you what has to happen. So first of all, the mirror equation. We have 1/DO plus 1/DI is equal to 1/F. And now you just solve for DI. So subtract the 1/20th to the other side. Now 1/10 is the same thing as 2/20ths. So 2/20ths minus 1/20th is 1/20th. And then take the reciprocal here. The image distance ends up being a positive number. It's positive 20 centimeters. So this then means that the image forms in front of the mirror and it's then therefore real. Notice that the image forms in the same location as the object, and that's actually at the center of the sphere. This is my light bulb demonstration. I'll draw it out for you in just a moment. We still have to calculate the magnification, however, and that's equal to the following: negative DI over DO. And notice that you end up with -1. So the 1 obviously means that the image is the same size as the object. And what do you suppose the negative sign means? It means that the image is inverted. That then therefore gives us the following ray diagram. This is the light bulb demo. Okay, so now we have right here once again our spherical concave mirror. Here's the optical axis like so, and then right here is the focus, we'll say. This distance here is 10 centimeters. Therefore, here's another 10 centimeters, and then therefore the object is right here at the center of the sphere. And then to form the image, I'm just going to draw here 2 light rays. Okay, a light ray, first of all, parallel to the axis like so. That then reflects through the focus like this. And then just draw the second light ray backwards. That is through the focus like so. That then reflects parallel to the axis like this. And if you do this carefully enough, as I've been careful to do so here, boom. Right there is the real inverted image. Notice that the size of the image is the same as the size of the object. This is the center of the sphere. So this is what I was attempting to do in my light bulb demonstration. Basically, the light bulb was placed upside down inside of its box right here at the center of the sphere, and then you see the image right side up on top of the box like so, and the image size is the same as the object size. Okay, okay, now let's go ahead and get closer to the mirror. These are situations that you haven't seen yet in parts B and C. Okay, so now in part B, we're taking the object distance and we're setting it equal to the focal length. That is, we're taking the object and we're placing it at the focus. The object distance here is given to us as positive 10 centimeters. Okay, let's just calculate out what happens first by using the mirror equation. So I have 1 over dO plus 1 over di is equal to 1 over f. Subtract the 1/10 to the other side. And notice what happens when I do. I end up with 0. So then therefore, if you take the reciprocal to find the image distance, you end up with the image distance being undefined. It's infinity. This means that there is no image. Now, what could that possibly look like? Well, watch this. This is the diagram you haven't seen yet. Okay, so right here is my mirror, optical axis like so. Right here is the focus. And then we're taking the object here and we're placing it at the focus. And now I'm going to go ahead and reflect 2 light rays off the mirror. The first light ray is the light ray that we always choose first, and that's the one that's parallel to the optical axis like so. And this then reflects through the focus like this. But what about a second light ray? I can't use the light ray, for example, up here on the top diagram that passed through the focus, because in this case, if I did, it wouldn't even hit the mirror. So then therefore, what light ray do I choose? I choose one of the light rays that you saw in my derivation of the mirror equation earlier. That's the light ray that goes from the tip of the arrow and then strikes right here at the center of the mirror. This light ray is easy to reflect because right here is the angle of incidence. And then therefore, all that I do on the other side of the axis itself, that's the normal line, I just reflect at the same angle. Like so. Notice that these 2 reflections are parallel. So because these 2 light rays here are parallel to each other, let me spell that a little bit better for us. There we go. Because these 2 light rays are parallel to each other, they do not converge over here somewhere to form an image, nor do they appear to be diverging from somewhere here behind the mirror. So therefore, there is no image. After I complete part C in just a few moments, then I'm going to have you take a look at part 2 of my concave mirror demonstration. That video that I've posted for you in the folder, it's basically this example. But before we do that, here's now part C. Okay, so now lastly here for part C, now we're taking the object and we're putting it really close to the mirror. Notice that it's closer to the mirror than the focus. Okay, once again, first of all, just follow the math. So 1 over dO plus 1 over di is equal to 1 over f. Subtract the 1/5 to the other side. And then mathematically here, this is 1/10 minus 2/10, which is negative 1/10. Therefore, when you take the reciprocal, the image distance here is negative 10 centimeters. So the image forms behind the mirror and it's virtual. Now I'm going to calculate the magnification. Just be careful of your negative signs. This is negative di over dO. And this ends up being positive 2. So you end up with an upright virtual image that is magnified. This is the ray diagram now for a compact makeup mirror. For those of you that use one, when you hold the mirror in front of you, you are closer to the mirror than the focus. So you see an upright virtual image that is magnified. That ray diagram now looks like this. Okay, so here's the focus. This is 10 centimeters. So then therefore 5 centimeters is like that. Right here is the object. And now to find the image, I use the same 2 light rays that I did in part B's diagram from a few minutes ago. First light ray, parallel to the axis, reflects through the focus. Second light ray, down to the center of the mirror, here's the angle of incidence, reflects at the same angle. Like so. Notice that the two light rays here and here are diverging from each other. So if they're diverging from each other, they look as if they're coming from behind the mirror. Take the two reflections and extend them back behind the mirror, like so. And there's the upright virtual image that's behind the mirror. This distance here, the image distance, is 10 centimeters. The negative sign means that the image forms behind the mirror. So you see an upright virtual image that is magnified. So when you use a compact makeup mirror and you're holding it in front of you, you are here and the focus is actually behind you, such that you then see an upright virtual image that's magnified. Okay, now I'm going to go ahead and conclude this video here. Immediately, however, go ahead now and take a look at the concave mirrors demonstration video, part 2.